All right, let's talk about something that can go very, very wrong when you're working on your car. Modern vehicles, they're basically computers on wheels. And that means one wrong move, one little slip up with a simple wire, can literally cause thousands of dollars in damage. So think of this as a critical warning for every DIY mechanic out there.
And get this, that's a quote from a professional automotive instructor, a guy who teaches this for a living. So this isn't some made-up scare tactic. It is a real, super expensive, and honestly, a frustratingly easy mistake to make. He's learned the hard way, so we don't have to.
So that's the big question, right? How does it even happen? How can one little pin, one simple wire, just completely fry a car's electronic brain? And more importantly, how do you make sure you never do it? Well, the answer is all about understanding these tiny, super fragile parts that run the whole show.
So let's jump right into that first simple but oh so expensive mistake. To really get a handle on the risk, we first have to know what it is, exactly, that we're about to destroy. Okay, at the heart of the problem is this little component called a driver. The best way to think of it is like a tiny, super fast electronic gatekeeper inside the car's computer. Its whole job is to open and close, letting just the right amount of power or ground flow out to a part, like a sensor or a solenoid. But here's the catch. That little gatekeeper is incredibly delicate. It's built to handle a very specific, controlled little trickle of electricity. If you accidentally hit it with an unrestricted flood, it's instantly fried.
So the first tool that can cause this whole mess is the good old jumper wire. Now, the wire itself isn't evil, but the danger comes from not knowing one of two very basic ways a car's computer actually controls something.
And this slide lays it out perfectly. It all comes down to polarity. Is the computer sending out positive power to turn something on, or is it sending out a negative ground? In a power side switch circuit, the computer provides the power. But in a ground side switch circuit, the component always has power, and the computer just provides the ground to complete the circuit and turn it on. You absolutely have to know which one you're dealing with.
So here's the disaster scenario. Let's say you're working on one of those ground side switched circuits. That wire is just waiting for a ground signal from the computer. But you don't realize that, and you connect your jumper wire to battery power. If that little driver inside the computer is active, if that gate is open, bam, you've just sent a tidal wave of current straight back into that tiny, fragile electronic gate. And it's toast. It happens in less than a second.
And don't even think for a second that a fuse is going to save you. As the instructor points out, the amount of current it takes to fry a driver is way, way less than what it takes to blow the fuse. By the time that fuse even thinks about popping, the damage to the computer's already done. See, the fuse is there to protect the wiring from catching fire, not to protect the delicate electronics at the end of it.
Okay, let's move on to our second dangerous tool, the T-pin. Now, these things are super useful for back probing, which is just testing a circuit without having to unplug everything. But their simple all-metal design hides some really sneaky, really destructive risks. There are basically two main ways this goes horribly wrong. First is accidental grounding. You stick a T-pin into a wire that's supposed to be getting power from the computer, and then that little pin leans over and touches a metal bracket or the engine block. Well, you've just created a dead short to ground, and poof, there goes the driver. But the second way, that one's even more clever.
And this is a classic mistake when you're trying to save a little time. You stick two T-pins into the same connector so you can test two wires at once. But you get distracted, the pins pivot just a little bit, and the metal shafts touch. You've just created a direct short between two different circuits, completely bypassing whatever component was supposed to be in the middle. And just like that, you fried another driver.
The advice from the expert here really couldn't be any clearer. The risk is just way too high. It doesn't matter how hard it is to get to that connector, using two pins at the same time is a gamble that you are going to lose eventually. It's one pin at a time. You take your measurement, you pull it out, and then you test the next one.
Okay, enough with the horror stories. We've covered the dangers, but you have to do diagnostics. So how do the pros do this day in and day out without a pile of fried computers in the corner? Well, it all comes down to following a very strict set of rules and, you guessed it, using the right tools for the job.
These are basically the 3 golden rules. First, look before you leap. Always use a multimeter to see what voltage is on a wire before you even think about applying your own power or ground. Second, like we just saw, one pin at a time, no exceptions. And third, while a T-pin might get the job done, there are much safer alternatives. And this is what the pros use. See that? An insulated back probe.
It does the exact same thing as a T-pin, but that insulated sleeve means it can't accidentally lean over and touch a metal bracket and cause a short. This one simple design feature just eliminates one of the biggest risks we talked about.
Now this right here is another hidden killer, your test light. A modern, computer-safe LED test light draws a tiny amount of current, about 20 milliamps. That's a little trickle. But that old-school test light with the light bulb in it, that thing can draw 300, even 500 milliamps. That's not a trickle, that's a fire hose of current. And it's more than enough to completely overwhelm and destroy a driver that was only designed to handle about 150 milliamps for a relay.
So if these methods are so incredibly dangerous, you got to be asking, why would anyone ever use them? Why not just use the tools the car manufacturer tells you to use? Well, the answer really comes down to necessity and the cold, hard reality of working in an independent repair shop.
This example of an EGR solenoid on a Honda is just perfect. This part is buried deep under the intake manifold. Now, the by-the-book procedure is to take it all apart and test the solenoid on the bench. But what if the problem is that it's just sticking a little bit? The act of unbolting it could shake it loose, and suddenly it tests perfectly fine on your workbench. The only way to find the real problem is to test it while it's still bolted in the car, where it lives, by tapping into its wires.
Now, the factory-approved way to do this uses these special breakout connectors. They're totally safe. But they're also unique to each car model. If you're an independent mechanic working on 40 or 50 different brands of cars, you can't afford to spend tens of thousands of dollars on a massive wall of unique connectors, so back probing becomes a practical necessity.
So here's the real takeaway. Back probing and jumping circuits aren't shortcuts for beginners. They are advanced techniques that pros use because they have to. It's a calculated risk. They can do it safely because they first take the time to understand the circuit, they know the polarity, and they use their tools with extreme, focused caution.
And that kind of leaves us with a really interesting question to think about, doesn't it? As our cars get more and more complex, sometimes the most direct and, yeah, the riskiest diagnostic test is the only one that's actually going to give you the real answer. It just shows you that fine line between a dangerous shortcut and a necessary, expert-level procedure.